Ted from the Exoplanet Modeling and Analysis Center, and today we're going to do a tutorial for the radiative transfer code Pytmosph3R. This tutorial is going to be broken up into two parts. The first part is going to be a tutorial on how to install this tool, and then we're going to quickly go through a Jupyter notebook that was written by the authors. So, Pytmosph3R can be found on the EMAC website. I'm going to search for it here, and when we find it, we can click on code and it will bring us to the GitLab page for Pytmosph3R. So we can see here that it's pip installable. So I'm going to copy that pip command and go to the terminal. First, I'm going to activate my Conda environment. So first, notice my Python version. I've found that in later versions of Python, I have an even more difficult time getting this installation to go through. But I'm going to show you some troubleshooting that we're going to have to do anyway. So first we're going to paste in that pip command, and we are likely going to run into an error. So we see here there was a problem when pip tried to install the package MPI4Py. So we're going to get around that using Conda. The problem is that after we install MPI4Py with Conda, when we go back to using pip's not going to know that we've already installed it, and it's going to try again, and that will fail. So we're going to have to find a way around that. So let's start with our Conda install. Great. So now we can try to install Pytmosph3R again, but this will not work. So I'm just going to show you that we run into the same error once again. So the way we're going to get around this is we're going to ask pip to install Pytmosph3R without installing MPI4Py, and this is a somewhat tedious process. So what we're going to do first is we're going to do pip install, and we're going to add this keyword, no dependencies, so no deps. So this is going to install Pytmosph3R without any of its dependencies. So then what we're going to do next is we're going to run the command pip check. And we see here that Pytmosph3R depends on XOK, which is not installed. And it also depends on MPI4Py, which is installed, but that is not known by pip. So all we're going to do next is XOK. This is another, so XOK is written by the same authors as Pytmosph3R. So we are going to do the same no deps command, except here, instead of Pytmosph3R, we're going to install XOK. And then the problem with XOK is that the latest version is not backwards compatible with Pytmosph3R. So I've contacted the authors, and they have asked that I use version 1.1.1. So we're going to do XOK equals 1.1.1. And that'll install, and then we're going to do pip check again. And now we see that Pytmosph3R only requires MPI4Py. So we have everything installed that we need. So in the next part of the video, we're going to go through the Jupyter notebook. All right, so now we're going to go through the Jupyter notebook that the authors have written as a tutorial. So from the GitLab page, we can scroll down to the bottom and we are going to click on documentation. And on the documentation page, we're going to go to run as a Python library, and the quick tutorial can be found here. So this IPython notebook I guess you can run it in the web IDE. I have downloaded it, but once you've downloaded it, you can follow along with me. So I'm going to go to where I've downloaded it in my system. And I'm going to start Jupyter. So to run this notebook, we're going to have to first download quite a bit of data. I've already done it for the sake of time, but you will have to comment or uncomment this first cell as desired by your system. So I'm just going to start here with the imports. It will take quite a bit of time for you to download the data. So we're going to start with a simple model. We have to define first the parameters of the planet and star. So we give the planet surface gravity, a radius. The star, we give it a temperature and a radius. And we're going to define the atmosphere grid. This is a one-dimensional model with 100 layers. And then we're going to initialize the atmosphere and different objects that are part of it. So we have to initialize the observer, opacities. You see here that this atmosphere contains hydrogen, carbon dioxide, and water. And then we're going to initialize the model, and we're going to run it. So this is a one-dimensional model. It should run rather quickly. We can ask it to print out various parameters, and then we can plot it. So we see this is a fairly high resolution spectrum of this planet. And we can also ask for a lower resolution spectrum. All right. So now we're going to go to a two-dimensional model. It's a 2-day night transit. So this model, we're going to give it a day side temperature and a night side temperature. Similarly, this model is also water, carbon dioxide, and hydrogen based, though this is this model, we're going to give it 49 latitude points and 64 longitude points. We define pressure scale, and then we're going to initialize it. And now we're going to run this model. This one will take much longer to run. All right, and now we can plot it. This doesn't look too different from what we saw before. And then we can also plot it, specifying latitudes of the equator. So this gives us a color map of the temperature on this planet. This package also allows us to compare between two different models. and it will give us overplot of the spectrum, the change. This is a 1D model versus a 2D model, the two that we've run already, and how the models change based on the longitude that you look at on the 2D model. Now, Pytmosph3R can also deal with GCMs. This is everything that we've done so far can be used with the current version of XOK. The GCM section of this tutorial requires the version of XOK that we specified at the beginning of the video. So we can initialize this, similar water and CO2 and hydrogen model. This one with 100 vertical layers. All right, so we're going to plot this spectrum as well. All right, now we're going to do some GCM emission. So again, we're going to specify the radius of the planet, surface gravity, all the parameters of our model, star temperature, star radius. We're going to run that again. Great, so now that that's done, it took 11 minutes. So now that that's done, we can plot the results of this GCM simulation. We have planetary contrast here as a function of wavelength and as a function of phase. And then there's also this color map of the phase angle as a function of wavelength. We can also use Pytmosph3R to model more interesting profiles using different gases and aerosols. So we're going to make a water and carbon dioxide atmosphere. We're also going to include some water ice, some condensation. So we're going to initialize this hydrogen atmosphere background with water and carbon dioxide along with our aerosols, and then we're going to run this model. All right, and now we can check the results of this model run. And gives us these maps. Depending on the latitude and longitude. We can also look at the pressure as a function, the temperature as a function of pressure here. You can see that you have this inversion here, and then this other slight inversion. There are a lot of really, really interesting maps and plots that Pytmosph3R creates just by default. I encourage you to do this on your own and change some parameters around and see what you can get Pytmosph3R to create. We can also save these models. This might be useful if you want to load them into another program, possibly that you've created. We can write them out as H5 files. these H5 files can then also be read back into Pytmosph3R, which can be nice for saving time because it took a long time to run some of these models. So I really encourage you to go through this on your own and change parameters around and see what happens. This is a very interesting, this is a very interesting package. I'm just going to show you what can happen just with this one-dimensional model if we change some parameters around. So I'm going to rerun it here very quickly and plot the spectrum so we can remind of what it looks like. So this is our high definition spectrum, and we can see that this had a planetary temperature of 2500 Kelvin. But what if we want a more, what if we're looking at a rocky planet, something more in the habitable zone? Well, what if we put in 300 Kelvin as our input temperature? How does that change the way our spectrum looks? And we're going to run the model again and notice how the spectrum changes here. We still have that high resolution spectrum, but the flux here is much lower, and the lines that we're seeing are very different. So I encourage you to go through this on your own, change the parameters around. It's a very, very interesting package with a lot of plots built into it. All right, thank you.